NIT Jaipur, and my email ID I am writing at mnit.ac.in.
Yeah.
So if you'll have any questions, you'll be mailing me this, and let's start our, um, learning the foundations of deep learning. You must have heard from the previous professor that he's talking about if you have large amount of data set, then it is good to go to deep learning. So what is this deep learning? Okay, so to start with, this is just a snapshot of from where we started and kind of where we are now. So we started in the 40s when McCullough and Pitts designed the artificial neuron, which was trying to work as a human brain cell, which is also called a neuron, works. So what was the idea? That the cell must receive certain inputs, as shown here, and depending on how strong are the inputs, it must it must be excited to a level that it gives some signal for some organ to function. So if we are building it as an artificial neuron, then how do we decide how the inputs will go? How do we decide what is the threshold which will activate the function, and then how do we decide what should be the output? So idea was a artificial neuron was born, but in this artificial neuron there was no learning. We have to set the parameters and the inputs, and then according to what was the expected output, you have to kind of physically learn the neuron. So then many people simultaneously started working on imparting the capability of artificial intelligence to machines. So, what intelligence is associated with this human brain? So, they started thinking, can machines also work intelligently? By this time, machines were working very nicely on huge amount of data, and they were very computationally very efficient compared to humans. So, in 1950, Alan Turing devised this Turing test that if an interrogator is sitting in front of a screen, and behind the screen there is a machine and a human being, and if he is asking some questions and he cannot decide whether the answer is coming from a human or a machine, then the machine passes the Turing test. So it was devised in 1950. And at the same time, this artificial intelligence thought came up that can machines think? So there was a workshop held in Dartmouth University, and there were 4 or 5 groups. They were started working on that, and in the 50s, 1956, birth of AI happened. Now this AI is the birth of artificial intelligence word came up, and John McCarthy gave this word that we can impart artificial intelligence into the machine so that the machine can work like the humans can work. That is, the machine can think like a human thinks. So when we started this neuron, the neuron was not learning anything. But in 1957, Rosenblatt devised this perceptron, which had the capability of learning. And later on, many models came up, like Adeline, which was at Stanford, which was adaptive linear expression something. And then later on there was a dip in this burst into neural networks and artificial intelligence, because in 69 Minsky and Peppard said that your neurons, which you were perceptron, which you were defining as they can solve any kind of problem perceivable by the humans, it can solve only linear problems. So what are linear problems? For example, we have two classes. One I am denoting as blue class, and another I am denoting as red class. Then both are linearly separable, and I am able to find out a boundary which separates the two classes. So such kind of problems are called linear problems. So they identified that the perceptron can solve only linear problems. So it is not good, and there was a huge dip because it was advertised that now we can solve any kind of problems. What are non-linear problems? Non-linear problems are as shown on the screen, something like this. This is usually it is shown with the help of a XOR problem, that you cannot separate it, the two classes with a single separating plane. You need at least two planes. This is also a non-linear problem, that one class is enclosing another class. That is, if the classes have convoluted boundaries, then how do we separate that? So there was a huge dip in this, but later on, multi-layer perceptrons were devised and they were able to solve the non-linearity problem with the help of non-linear activation functions. We'll understand these terms by starting with the artificial neurons. So the second golden age came with the back propagation of errors algorithm, again by Rumelhart and Geoffrey Hinton. And of course, we have non-linear activation functions. And instead of a single layer perceptron, now we have multi-layer perceptrons. And presently, where are we started with machines which were automation started with machines which were computationally very efficient. Then we started with that, let we give artificial intelligence to machines, and now we want the machines to generate content, that is generative artificial intelligence. That is, they should be able to generate text, they should be able to generate images, they should be able to generate videos like the humans can do, they should be able to draw paintings, like they should be able to do the creative things also, the artistic things also that the humans are doing. So to start with, what is a neuron? You can see the first model was like a brain cell works like this, that there is a nucleus and the brain cell receives signals from various organs through dendrites. Now, when the sum of all these signals is above a threshold, for example, if I touch a hot plate with my finger, my brain will give me a signal to immediately withdraw the finger if it is very hot. And if it is tolerable, then I can keep the finger. So that is what I mean by threshold, that if the input is beyond my tolerance level, then my nerve cell excites and it gives the signal that you have to withdraw the hand. So that signal is output, which is given to the organ through the axon. So we mimic this McLuhan pit by this cell, which we call the neuron. So this is the cell body corresponding to the artificial, that human cell. It is receiving input in the form of X. Now, in machine learning, X denotes the input, and the input is multidimensional, so it is denoted with the help of a vector, and the column major form of vector is used. So for example, the input is you want to classify apples and oranges. So to classify the fruits, the input you can have the size of the fruit, the color of the fruit, the length of the fruit, the texture of the fruit. So this constitute multiple dimensions. So for example, x1 is size, x2 is length, x3 is color, like this. So this input becomes, let's say we have d dimensions, so we denote x as d dimensional, which I denote like this. You can also write it as, okay. Now, what importance I have to give to a particular input, that we decide with the help of the corresponding weights which are shown here, W0, W1, W2. Now, we are we are multiplying these weights with the corresponding input. So this weight is also a vector which has the same dimension as the input, because you can multiply two vectors only when their dimensions match. So by multiplication, I mean that you are doing either X transpose into W and you get an output which I call Y. So Y is the output in machine learning. Okay, this is the output which we are here calling a class, also called label. This is X is the input and W we call as parameters. Okay. So either you are doing this or you are saying you can write that it is W transpose X, which is equal to Y. So this is kind of dot product W naught W1 till WD X naught X1 till XT. Is this okay? Can somebody say that you are understanding this dot product? So you can also write it as X dot Y, X dot W, and which gives you a Y. So what will be the value of Y? Y will be a scalar value because we are doing dot product of two vectors, which gives us a scalar value. Is this all right? So now what I do is either I take this Y as output as it is, or as I said, what I am doing is I am applying a function over this Y, because Y will be a real value. And I say if the function is, for example, I say it is class 1 if Y is greater than 0 and it is 0 otherwise. So that means I am now doing a classification where I am saying if Y is positive, then it is probably apple, and if Y is negative, it is orange. Is this okay? So let me show you with the help of an example. So let's say your data is something like this. X1, this is 1, 2, 3, 4, and 5. This is 1, 2, 3, 4, and 5. And let's say your class were like this. This is one class, and there is another class which is, let's say, 3, 4 is another class, 4, 4, and then 3, 4, 3, and 4, 5 maybe. So if I can draw a line like this. So what is my boundary, linear decision boundary, which is separating the two classes is, I can write this. This is x1, this dimension, and this is x2. So I can say that 5x1 plus 4x2 equal to 20. Let's test whether it is true. So I pick a point on the boundary, which is 4, 0. I substitute here. So 5 into 4 plus 0 into 4 equal to 20. So this is true. So this lies on the boundary. Now let me check the other point which is given here, which is 0, 5. So this is 5 into 0 plus 4 into 5, which equal to 20. So this is also correct. So that means my boundary, which I am writing as, let me bring it here, minus 20 minus 20 plus 5x1 plus 4x2 equal to 0 is 0 if x1, x2 lies on the boundary. Because when it is on the boundary, then my point belongs to both the classes. Now, I can write it as minus 20 into x naught plus 5x1 plus 4x2 equal to 0. So what is this x naught? X naught, I will extend the x by 1 so that my offset, which is minus 20, remains 20. So now what I am doing, I am making x from 2 dimension to 3 dimension, which is 1 and then x1 and x2. And correspondingly, W is also 3 dimensional, which was already 3 dimensional, W naught, W1, and W2. So W naught is the offset to make to keep W, because my equation is coming as y equal to W transpose X. So I extend X by 1 so that when it gets multiplied by W naught remains as it is. Now, do you understand this? Someone? You are getting this boundary. Now let's check what happens to this point. If I substitute this value into the boundary equation, so here is my equation. I substitute 2, 1 here. So what 2, 1 is giving me is minus 20 because x naught is 1 plus 5 into 2 plus 4 into 1. So what this evaluates to minus 20 plus 10 plus 4, which is less than 0. So this is a negative class. Now let's test it for 1, 1 also. So this will be minus 20 plus 5 plus 4 also less than 0. And if you will test for all these classes, you will get a negative sign. And when you will test it for this side of the class, then you will, let's say the point is 4, 3. So if I minus 20 into 1 plus 5 into 4 plus 4 into 3. So this is equal to minus 20 plus 20 plus 12. So this is greater than 0. So this is a positive class. So now you understand that one side of the boundary is a positive class and other side of the boundary is a negative class. And when the point is lying on the boundary, it is equal to 0 because I am representing the boundary with the normal, and the normal is pointing in the direction of the positive class. So if something is lying on the boundary, then that vector and the boundary will evaluate because they are at orthogonal. So the scalar dot product will be equal to 0 because it is the cos of the angle of the two vectors. So you will get a 0 if the vector and the normal is lying in the same direction, it is a positive class. If they are lying in the other direction, it is a negative class. So this is your W. So what we are trying to do with the neural networks is X and Y is defined by the problem. That is, input is defined by the problem. It is a supervised learning. So corresponding to every input, I have a output also. So what do I mean by this is something like this. That when I'm giving a training data, so this is the training data which is on to your screen. How do I define the training data? I define it with the help of X vector. Now, every point is a vector. So when I am talking of this point, then it is this point, let's say. So this is 1 extended. So this is 1, 1, 1. The second point is 1, 2, 1. Now, when I am describing the complete data set, then every vector becomes a row in the data set. So I get x1 here, x2 as a row, that is X transpose, and the nth data point here. So now my X becomes a matrix which is n number of samples and each sample is d-dimensional. So this capital X in machine learning is denoted as n by d. This is my training data X input. Corresponding to the X, I have Y also. So now in this example, what will be my X matrix? The first point is 1, 1, 1. Corresponding Y is simply a vector corresponding to every input. There is a class which is saying it is a negative class, minus 1. Then I have 1, 2, 1, which is also minus 1. Then I have 1, 1, 2, which is also minus 1. Then I have 1, 1, 3, which is also minus 1. Then I have the second class, which is a positive class. I have 1, 3, 4, which is plus 1. ये y आप extended रखेंगे. Then you have 1, 4, 3, which is also plus 1. And similarly, you have 144, which is plus 1, then 145, 145, which is a plus 1. Is this okay? So X may how many samples are there? There are 1, 2, 3, 4, 5, 6, 7, 8 samples. So I have 1, 2, 3, 4, 5, 6, 7, 8. So it is 8y, and every sample is 3 dimension. And what is y? Corresponding to every x, there is a single value which is denoting the class. So it is 1 dimension. And how many y's are there? There are n y's. So this is n by 1 vector. Is this clear? Is this clear? Now what I do in this problem is that I have to learn this W. ये W मैंने जो आपको अभी दिया, ये तो मैंने एक इसमें देख के एक W ले लिया कि because it is classifying, it is it is doing the classification correctly. But how do I get this W? There can be other W's also. For example, oh sorry. For example, uh, this was separating it, but there can be, this can also separate it, this can also separate it. I can have other separations also, like this. So how do I choose this W? I am not choosing this W. This W my network will learn. Okay, this W my network will learn. So what we do in neural networks is we have the input, we have the output. What we do, we learn the parameters. What are the parameters? W is the parameter. So that uh, single layer perceptron was this, which is onto this screen, that you have a single layer node. You have inputs. These inputs are called x12, let's say 3 inputs. Corresponding to every input, there is a weight. So I do x1 into w1 plus x2 into w2 plus x3 into w3. This is the dot product of x and w. The summation is done here, which is a dot product. We apply a function which is called activation function, and you get an output. Okay, this bias term is called your W naught. So here, because as I said, that this single layer perceptron is capable of only solving linear problems. But life is not linear. We have non-linearity. So how do we solve that? With the help of multi-layer perceptrons. What is a multi-layer perceptron? The input we call as the input layer, the output we call as the output layer, as in the perceptron. Now we have intermediate layers also, which are not visible to us. So we call them as hidden layer. For example, onto your screen, there is only one hidden layer. Is this okay? So now from a single layer perceptron, we are coming to multi-layer perceptron. There can be multiple hidden layers. Number of nodes in the hidden layers can vary, like I am drawing here, and this is the out. So here, this will call as the input layer, this will call as the output layer, and these will be the hidden layers. Okay, every input node is connected with through a weight to every other node in the next layer. Like this. So this is called a fully connected network. Okay, so you will observe weights. So this is a multi-layer perceptron, and every layer in every intermediate layer also, every node is connected to every other node, and finally all these are connected here. So ये आप पूरा नहीं बना रही हूँ, but you understand the concept. So, and at what is a node? Node has a capability which is summation of all the inputs and the corresponding weight. And there is a function over the summation which is called the activation function. So this is a fully connected network on your screen. Now, when there is a weight, the weight is coming from this first node to this first node. So I'll write it W11. Then from which node to which node? So W first node to second node in the first layer. So 1 is the subscript. Okay. So then first to the mth node in the first layer. Now this will be the weight from the second node to the first node in the first layer. And like this, you do the nomenclature weight from the third node to the first node in the first layer. And then here the weight is from the first node to the first node of the second layer, from the first node to the second node of the second layer, like this. I hope this is clear. So if there are n nodes here and there are m nodes here, the weight will be a matrix which will be n by m. Is this okay? So now it is shown here. You can see that for this node, because we are saying that now we have multiple layers instead of a single layer, and the input initially there was a single layer, so I called the input as X. But now when the input is going to a layer and it is doing applying an activation function over it, which is become the output of the activation function is becoming input for the next layer. So now we are denoting the input with this A word, which is the activation function, activated output, because now we have multiple layers. So for this activation function A1, the input that is coming here is, you can see that W11 into A1 from the 0th layer, which is this term, plus W12 into A2, which is this term, and plus W1N into A3. And the bias term it is separately writing because it is not using W0, but you have to make it part of this. So you can write here W from the uh, 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 first layer to the from the node 0th node, and from the 0th output to the फर्स्ट नोड यहाँ पे. तो इस बी नॉट को आप W10 भी लिख सकते हैं, एंड इनटू आपके पास में क्या आएगा, इनटू आएगा A0, which is your bias work. Is this okay? So now we do a summation and I am applying an activation function. Here the activation function, this is a special symbol for sigmoid. We'll see what is sigmoid. So now you write every output is this weighted sum. So what it is doing, this weight which is going to the first node is becoming one row, and it is getting multiplied with all the inputs. So the input is here, so it is getting multiplied with this dot product which I told you, and plus because bias यहाँ पे अलग से लिखा हुआ है, इसलिए we are adding the biases which are going to every node. And because if you take it part of W, then you will append it as W10, and you will write here B00. So then it simply this A00, then you don't need this part. Is this all right? So we apply a activation function on this and we get the activated output A1. This A1 becomes input for the next layer, and the same process repeats. Now you see that every connectivity of m by n nodes here is, it needs how many parameters? It needs m by n parameters. And if there are n layers, we have m by n into n parameters. So that's why it is said we can define the a two-layer multi-layer perceptron can solve any kind of non-linear problem. Of course, the number of iterations it will require will be large, but you can have many hidden layers in between, and we'll see how the hidden layers help us. So, how many hidden layers we want, how many nodes in the hidden layers we want, these we decide. Decide them as heuristically. That's why they are called hyperparameters and not parameters. What we learn from the network are called parameters, which are W. What is defined by the problem is the input and the output. Hyperparameters is how we are designing our network, that is how many nodes will be in the input, that will be decided by the dimensionality of the input. How many nodes in the output, that will be decided by the number of classes that we want as output, and how many layers we want in the network, that we are deciding. How many nodes in the layers, every layer can have equal number of nodes, and we can have different number of nodes in the layers also. To simplify the computations, usually we keep the number of nodes in the hidden layers as same. I hope this is clear. So we come to the activation functions. So as I said initially, the activation function with which we started in the linear classification problem was we were applying a threshold over the summation y, which was w transpose x. And I was saying that if it is greater than 0, then the class is plus 1. And if it is less equal to 0, then I was saying class is minus 1. Now, what is the problem with this? It is called a step function. So the step function is you need a threshold value. So this threshold value, the sum which is coming. So if it is greater than this value, then I am saying the class is plus 1. And if it is less than this, then I am saying, let's say the class is minus 1. So this is a hard threshold. So you see that with a small change in input, I am in class which is minus 1, and with the small increment I am going to a class which is plus 1. So how do I decide this threshold? So that is a problem, because this step function is a non-differentiable function, and we need differentiable functions uh, uh, as activation functions, because we are kind of solving in this network, we are learning, and the learning is happening using iterative process. And when do we stop the iterative process? We are optimizing a function which is called a loss function. Now, what is a loss function? As an aside, let me tell you this. Loss function is that when in this training example, when do I stop the training? I stop the training when I have learned a W where every W transpose X is giving me the correct corresponding Y. That means now the learning is complete, because this W is doing the job. So I have learned. So how do I decide I have learned? That what I get as y output, let's call it as y tilde. And what was the desired output? That was y. This is error. And the error, all the inputs should be equal to, what is the minimum of value of error? They should be equal to almost 0. Okay. But when I do a summation of y tilde, that what I predicted, minus y, that is why these are i's over all the samples, and if some of the values were positive and some were negative, then it might come as 0, though the error was large. For example, error for first sample is -5, for second sample is 5, for third sample it is 10, and for fourth sample it is -10. I do a summation, I'll get a 0 error, which is not the case because the error is very large. So what I do instead, I do a absolute value and do a summation of that. But this is also not the good idea, because this is not a differentiable function. An error, we need a differentiable function, because we follow the algorithm which is called gradient descent. Now, what is gradient descent? Let me quickly tell you that gradient descent is, for example, you are on top of a hill and you want to go down, and the terrain is not visible to you. So it is very foggy and you are standing somewhere. So what you will do, you'll take a small step size in the direction where the slope is decreasing. Okay. So for example, मैं यहाँ पे हूँ, मुझे नीचे जाना है, तो मैं क्या करूंगी, एक स्टेप छोटा सा इधर लूंगी. So now my view will change from this place to this place, and I'll again take a small step in the negative direction of the gradient. What is gradient? The slope. The slope here is this. To come to the bottom, I am taking a small step in the negative direction of the gradient. If I am on this side also, then I am doing this. So this is kind of that your error function is, we want error function which is convex. What is a convex error function? Which has only one minimum. How do we know that? Because it behaves, it is like a saucer. It is like a saucepan, where if you roll a ball, it will come and become stationary only at the bottom. So convex function, how do we define it mathematically? If we join any 2 points on the convex function with a straight line, then the straight line always lie above the function. What do I mean by this? Let me draw it again for you. Now choose any 2 points on this function. Let's say this is x and this is fx. So let's say this is x1 and this is x2. If I join any 2 point on this function, what is this point? This is fx1. And what is this point? This is fx2. With a straight line, then every point from x1 to x2, the function value of, let me draw it again. How do we define a convex function? Is like, this is a convex function. How it is defined? Pick any 2 points on the function. The function between these 2 points will always lie, function value will always lie below this line. That means the function is never crossing this line between these 2 points. What happens if it crosses this line? That means there are multiple minimum and maximum values, which is not a convex function. So mathematically we say that this is a convex function. I'm sorry about the multiple drawings, but you will understand it now. So this is, let's say, A, and this is B. On this x and y-axis is fx. So what is this? This is fa. What is this? This is fb. So you choose any point which is, let's say, t times a plus 1 minus t times b. So now when I choose this point, the function value is this, which is f of t times a plus 1 minus t times of b. This will always be less than, what is this value on the line? This is t of fa plus 1 minus t of fp. Okay, that means less than equal to. Then it is always a convex function, and t is varying from 0 to 1. When t is 0, then we are at, let's say, b, and when t equal to 1, we are at a. And we vary this t with the step size And at every point, if we get choose any point, this is the function value, this is always less than the point on the line joining this is the function value. So we prefer these kind of convex functions as loss functions because they are easy to optimize. Why? Because they have a single optimal value. Because it is loss, it is a minimum value. If we are maximizing something, it is a concave function, which is a negative of convex function. Again, maximization of a convex function is easy because there is only one optimal value. If it is a non-convex function like this, then there are multiple values. If you start somewhere here, you will get stuck here, you cannot come out of it while the optimal value is here. Okay, so you understand this. So what we need is a convex function, and the convex function as an error function is a differentiable function, and it is a continuous function. And we, when we differentiate and equate it to 0, we get the optimal value. So the step function was not a convex function. So in the when the back propagation algorithm with multi-layer perceptrons and a non-linear activation function, that non-linear activation function was your sigmoid activation function, which is shown on your screen. So this sigmoid activation function is represented as 1 over 1 plus e raised to power minus x. Now, if I take x as 0, then what will happen? It is 1 over 1 plus e raised to power 0. So this is 1 over 1 plus 1, which is 1 by 2. So which is kind of 0.5 here. When I substitute it with a very large value, large positive value, then e raised to power infinity is equal to 0. So you get, which is 1. So for large positive values, it saturates to 1. And for large negative values, when you substitute it by minus infinity, so this becomes 1 over 1 plus e raised to power infinity, which is 1 over infinity. So this saturates to 0. So for large negative values, it saturates to 0. For large positive values, it saturates to 1. So it fulfills the capability of classification, that if you are very sure you have a large positive value, you belongs to a positive class. If you have a large negative value, you belong to a negative class. If your value is 0, then you are 50-50 that whether it is a positive class or it is a negative class. And it is a differentiable function, and it is a continuous function, and it is a non-linear function. So now every node, if we apply the threshold, the activation function as sigmoid, it becomes a non-linear activation function. Now what is the problem with this sigmoid? The problem is that it gets saturated to, for large positive values it will get saturated to 1. So when I differentiate in this region, the differentiation becomes 0, almost 0. And for this region, when it saturates to negative values also, this differentiation becomes 0. So this is called a problem of vanishing gradient. So this was identified, and then later on, to overcome with this, in the early 2000s, we came up with the ReLU activation function. The ReLU activation function is shown here. What it is, it says that the output should be, if it is a positive value, the output should be the same value. If it is a negative value, we truncate it to 0. So now, though it is a not a continuous function because there is discontinuity here, but f dash x becomes equal to 1 when it is x is positive, and when it is less than 0, then we say that this is also equal to 0. So we take it as a differentiable function, and because the derivative is coming as 1, so there is no vanishing gradient problem. Is this okay? You are understanding the vanishing gradient problem? Anybody? अभी तक की बातें समझ आई हैं आपको? कोई बता सकता है? एनीवन मैसेज कर सकता है? मुझे आइडिया तो हो समझ आ रहा है। Yes, ma'am. Okay, very good. So now let me rub this. So you got the ReLU activation function also, and these functions are convex. You can prove that, and because this sigmoid activation function gives us the class as 0 or 1. If you are interested in the class as -1 and +1, then you have a tan h activation function, which is this: e raised to power x minus e raised to power minus x divided by e raised to power x plus e raised to power minus x. And this kind of gets interchangeable. You can go from tan h to sigmoid and from sigmoid to tan h. But this also has the problem of vanishing gradient, as you can see in the diagram. Now, if you have multiple classes, then you have a softmax function. Whatever softmax function is doing is, it is the at the output you have every node will have whatever is the input coming, e raised to power that x, e raised to power its corresponding x1, x2, x3, like this. So to convert this value into the probability, that which class has the highest probability, we divide every value with the summation of all these values, this plus this plus this plus this, so that now the output nodes will have a probability, and suppose there is a and which adds to 1. So probability of this is, let's say, 0.7, and this is 0.1, this is 0.05, and this is, let's say, 0.25. So this adds to 1. So we know what is the class. This class has the maximum probability. So we'll classify it as this class. So this is a softmax function which can handle multiple classes also. So now let's understand why we are doing multiple, why we are interested in designing multi-layer perceptrons conceptually. So let's say we have input which is a 2 by 2 image, so which is kind of this. So as I said, the input is a vector, so I'll convert this input into a vector by flattening the image. What is flattening the image? The first row will become this column. I'll append the second row below this, and it will become an input of 4 by 1. Is this okay? So now my input is, this is going here, this is going here, this is going here, and this is going here. This is flattening the input जो मैंने यहाँ पे किया, x1, x2, x3 and x4. Okay. So in the input layer, the first layer which we call as the input layer, every node of the input layer here is getting affected by only one pixel of the input image. Supposing my image was 256 by 256, so I'll flatten it out. My vector will become 256 into 256 by 1. And input में मेरे पास में कितने nodes होंगे? 256 by 256. And every input node has incoming input from a single pixel. So which is called its receptive field. So in the input layer, the receptive field you see, though the image size is 4 by 4, but the receptive field of the first node is this. The receptive field of the second node is only this pixel. Of this third node is only this pixel, and fourth node is this pixel. This is happening in the first layer. Now let's come to the node to the second layer, which I'm using a green signal now. So here the input is, this is getting input from this node and this node. Okay, the connectivity is showing you this. It is, as I said, it is connected to the other nodes also. For example, ये इससे भी connected है, let's say इससे भी, but उसका corresponding weight 0 है, इसलिए वो यहाँ पे दिख नहीं रहा, तो कॉम्प्लिकेशन हटाने के लिए मैंने वो कनेक्शन नहीं किया हुआ, मैंने वो कनेक्शन ही हटा दिया। कनेक्शन कहीं हटा हुआ है, दैट मीन्स इट इज a zero weight. I hope this is clear. So now you see that it is getting affected by two of the pixels. Which are those pixels? This node's receptive field was the first pixel, so which is this, and uh, this pixel, and this node's receptive field was this pixel. So the receptive field of the second layer becomes 2 pixels. Similarly, the receptive field of this node becomes these 2 pixels. For this node, it becomes these 2 pixels. And for this node, it becomes these 2 pixels. And in the arrows, I'm using weights only +1 and -1. So +1 is denoted by the black color and -1 is denoted by the red color. So -1 means that the pixel color is black, and +1 means the pixel color is white, and gray means it is 0.5. The pixel intensity is varying from -1 to 1, where -1 says it is a black pixel, +1 says it is a white pixel. So here in this second layer, let's talk about this node. Oh, why the eraser is not working here? Okay, let me use a different color so that. So let me talk about this. I'm talking of this node. This node. Now here in this node, this first is joined by a plus sign, so it needs, for it to be activated, it needs a on +1 value for this pixel. Now this is joined by a -1 weight. So I need this pixel to be off so that this node gets activated. So this off is shown by 0. So its receptive field is 2. And when will this node activate? This node will activate when this pixel is white and this pixel is black. You understand this? And similarly the rest of the pixels you can understand. So I am able to, now the receptive field of the second node goes from 1 pixel to 2 pixel. Let's see the third layer. In the third layer you see that this node is getting input from this node as well as this node, so the receptive field goes to all 4 pixels in this layer. So as you go deeper into the network, these we call the early layer. So early layer is dealing with the low level features. What are low level features? Single pixel. The second layer is joining the 2 pixels and maybe identifying a line. The third row is joining the lines and identifying corners. The fourth row are joining these corners and lines to form some object. So as we go deeper into the network, towards the end, we are going into high level features, which are called the objects. When we are in the low layers, we are dealing with the low level features, which are pixels. Next layer maybe lines, next layer maybe corners, next layer maybe joining the corners to form different shapes and then different objects. So finally, this network is capable of distinguishing a 2 by 2 image as a box, whether it is a box, whether it is a vertical line, whether it is a diagonal line, or whether it is a horizontal line. So conceptually, you understand why we need multiple layers. The early layers are identifying low level features. Then the other layers, hidden features, are combining those their receptive field keep on growing and they are identifying more high level features. And finally, we can classify objects. So this is an example of if the input is a horizontal layer, this network will identify it as horizontal layer. You can practice it. I'll be sharing the slides with you. So here is an example which says that if you are interested in digit recognition, you have a MNIST data set which helps you in identifying handwritten digits. So we have images of handwritten digits which are 38 by 38 size, I think. So now a one is broken into small line segments, and when we join these line segments we can identify it as a one. This zero also is broken into small line segments which are joining at different corners at different levels, as you can see here, and then combinedly we will be able to identify this. 9 consists of this and this, which are further broken. 8 consists of two loops. 4 consists of maybe different lines. So when there is an input image, we flatten it out. So here the number of nodes are like this, and then depending on which node is activated by which pixel, they combine and activate other nodes in the next layer. This keep on going, and then we are capable of understanding that it is 9. So we learned this network. How do we learn this? We learn this with the help of feed forward back propagation algorithm. What is this feed forward back propagation algorithm? Let me show it visually to you. So here is an example network. So output of this node, so you have two inputs, there are two layers, and there is a single output layer. So output, which is denoted by Y, of this first node is the activation function F1 applied on this weight multiplied by X1 plus this weight multiplied by X2. So you get this Y1. How do we get Y2? We get Y2 by applying F2 over this weight into X1 plus this weight into X2. So you get Y2. Similarly, you get Y3 by doing this equation. Then once I have Y1, Y2, Y3, I can compute Y4 and Y5. So how is Y4 computed? The weight which is connecting this node 1 to 4 into Y1 plus weight 2 to 4 into Y2 plus weight 3 to 4 into Y3. So I have a Y4. Similarly, I have a Y5 which is like this. So this is W15 into Y1, W25 into Y2, W35 into Y3. So once I have Y4 and Y5, I'll compute Y6. So Y6 is weight 4 to 6 into Y4, weight 5 to 6 into Y5, and you have a output because this output I can see. So the input is fed forward from the first layer through the hidden layers, and we compute a output. This is called the feed forward step in the algorithm. Okay, we are doing the feed forward back propagation algorithm. Now once you feed forward the values or every input through the network, you will get an output. Now corresponding to output you have an actual output. Let's call it y tilde. So you will compute error, and I am doing a square because a square is a convex function. Okay, and I'll take a summation of this error, and I'll take the average error, तो मैं इसको 1 by n से भी divide कर देती हूँ. This is the loss or the error. So you compute it. Now this loss I can see only at the output. Now how much change in this W, slight change, if I change it, how much it is affecting the loss? What small change in W is affecting this loss? And similarly, I have to identify how a small change in the weights is affecting the output. So why I am doing this? But because you remember this convex function, So what I have to do, I have to follow the gradient descent algorithm. What is gradient descent is, you initialize the weight to random values, all these parameters to random values, which we have to learn. Random values, because you can start anywhere. Now, let's say the random values gave me this point. So the minimum value is here. You can see that if this is x1 and a small increment here, which is x2, then this is fx1 and this is fx2. So when I differentiate it, I say that fx2 minus fx1 over x2 minus x1. This is the differentiation here, which I am calling the gradient or the slope. So differentiation in multi-dimension is called gradient, which is a vector. So differentiating the function with respect to all the parameters, with respect to, let's say, w0, with respect to w1, and with respect to wd. This is gradient of the function. Okay, because it is a multivariate function. Now the gradient here you can see is a positive value. Now to come to the minimum, I have to subtract something from the weight. So I take a small step in the negative direction. Small step. Why small step? अगर मैं बड़ा लूंगी तो अगर आप कहीं हिल टॉप पे हो और आप बड़ा सा जंप लोगे तो क्या होगा? It will be catastrophic. You will fall down and you will die. So here what happens is, if you are taking a big step, you might overstep the minimum. You might come here and then there is no acceleration, gravitational force here, so you keep on bouncing on the surface and you might go out of it without finding the minimum. So we take a small step at a time in the negative direction of the gradient. Now this gradient is, here it is positive, so I will update whatever W was there, I plus 1, as the previous W minus the gradient of the function in the negative direction, and a small step at a time, which is this learning rate or the step size. So previous W, I change by a small step size. How I will change? In the negative direction of the gradient. So positive था तो कुछ माइनस करना है, इस तरफ आपका ग्रेडियंट और स्लोप नेगेटिव रहता है, तो यहाँ पे अपने को इसमें कुछ ऐड करना है ताकि अपन मिनिमम पे आए जो 0 है. So we are always proceeding in the negative direction of the gradient, small step at the time, gradient with respect to W. Okay, you understand this? What I am saying is, what small change in W I should do, because I am starting at a random W, where, what will be the learned W when my error is 0? When my error is 0, when the magnitude of the gradient is almost 0. That is, फंक्शन को डिफरेंशिएट किया आपने और इसकी वैल्यू 0 है, तो आई विल गेट ऑप्टिमल वैल्यू, बिकॉज यहाँ स्मॉल स्टेप आप किसी डायरेक्शन में लीजिए, आपके कुछ इंक्रीज डिक्रीज नहीं हो रहा, द ग्रेडियंट वैल्यू इज 0. सो ऑप्टिमल वैल्यू इज एट 0. whether it is a maximum or minimum, we get by taking second differentiation, and if it is a positive value, it is a minimum, and if it is a negative value, it is a maximum. So you understand the gradient descent algorithm? You understand what I'm conceptually, you are understanding it? Hello? Anybody? Yes, ma'am. Okay. So Deepak, you tell me now, I need actually one more class to tell them this back propagation of errors.
Uh,
Because then it will be, otherwise it will be like, too complex for me to make them understand everything beyond this. I have to tell them the chain rule and then the updations and then the What do you suggest?
You can, ma'am, just briefly tell, then we will see whether we can accommodate one
Okay,
more lecture
okay,
or not.
yeah,
You can
yeah.
just briefly give them idea.
So I
Uh,
can give the idea here itself, that now what we do is we compute the error at the end. This is the error, and now we see that how what small change in the weight is bringing what change in this error. Means we kind of distribute this error towards all these nodes. And when the error, because the error we are not able to compute in the intermediate nodes, because we know only the output value corresponding to the input value, so the output will get at the end of the node. So this now the back propagation of errors happens. So how the back propagation of error happens is like this. So this error is connected with this node through this weight. So if I do a small change in this weight, what proportion of this input is weighted by this weight, and this is affecting this error. So I say इस error का इस node के जो change करूंगी with respect to this weight, वो कितना होगा? That error is corresponding to this weight into, let's say, this error. So यहाँ पे कितना आएगा corresponding to this weight into this error. Now इन nodes पे कितना आएगा? Let's see that. इस नोड पे क्या आएगा? दिस वेट इनटू जो यहाँ पे एरर आया था, प्लस दिस वेट इनटू जो यहाँ पे एरर आया था. So you keep on back propagating the errors like this, and then you update the weights. As I said, we are updating it in the negative direction of the gradient. This is the learning rate, this is the gradient. Okay, so gradient कैसे आएगा? मैं आपको यहाँ पे let me explain it with the help of my slide. So I said that your error is, let's say, let's take this example, that you have four nodes which are connected like this. So this node is connected to this node with the help of this weight and this bias, which is further connected to this node with this weight and bias, this node and this bias. So the output at this node is, let's say, a sigmoid function. The weight which is coming into this layer into the activation function which is from the previous layer plus the bias at this layer. For example, आपके पास में यहाँ पे जो आएगा वो आपके पास में क्या आएगा? वो आएगा W3. It is the third layer into activation from the second layer plus B3. Okay. So now I know what is this activation function. This activation function, let me, now this equation here, I write this term, the multiplication term, as Z. So Z is this WL into AL minus 1 plus BL. So for every AL is the activated, the sum and the activation function applied onto it. Let's say the activation function is sigmoid function, and you get a output which is Y. You understand this? WL इंटू AL माइनस वन प्लस BL, ये किसी भी नोड के ऊपर अप्लाई हो रहा है. तो इसको फर्दर जो आपके पास में A2 है, that is in terms of A1, so I expand it further. So AL minus 1 में क्या आ रहा है? ZL minus 1 आ रहा है. वो क्या है? WL minus 1 into AL minus 2 plus BL minus 1. एंड AL minus 2 कहाँ से में जो चीजें आ रही हैं वो आ रही हैं WL minus 2, AL minus 3, BL minus 2. So this is how the nodes are connected to each other. Now, if you are interested in knowing that this cost, which is the difference between your this is the error, which is also called cost, difference between what I was saying, the actual value and the computed value. Now this, when you want to know the effect of small change in AL onto this cost function. So this cost function is what? This cost function is coming in this cost function is coming in terms of your activated output, which is AL. So what is the activated output? That activated output is in terms of this ZL. So what it is saying, for example, you are interested, so you apply the chain rule. So let me remove my, just a minute. Let me remove this and try to explain you this. So I'm saying the chain rule is, if I do a small change in WL, it will bring a small change in ZL. Because what is ZL? ZL is WL into AL minus 1 plus BL. And this small change in ZL is bringing a small change in the activation function. And this is bringing a change in the cost, because cost is this activated output minus actual output. So if you want to differentiate this cost with respect to this W, so you are saying what small change in W is bringing what small change in the cost. Now this cost is not a function of W, but it is a function of this A. So I differentiate this cost with respect to A. Now this A is a function of Z. Again, it is not a function of W. So this is multiplied by differentiation of A with respect to Z. And now the Z is a function of W. So we differentiate it with respect to W. So this becomes a multiplication of the differentiation of the cost with respect to the activation function into the differentiation of the activation function into the differentiation of the input to the activation function, which is W transpose X with respect to the partial weight. So that is what is shown here in your figures when we are back propagating the error. So back propagation is when we are updating the weight. So here in this slide, you can see it is saying that the weight, previous weight gets प्लस क्यों हो रहा है? बिकॉज हमने एरर यहाँ पे क्या किया है? हमने एरर किया है when I do y minus y tilde. Okay, then when I'll differentiate this with respect to W, so this, let's say I do y minus wi xi. ठीक है, इसको जब मैं डिफरेंट, दिस इज माय एरर फंक्शन एंड ये 1/2n कर देते हैं, 2 बिकॉज स्केलिंग करने से कोई फर्क नहीं पड़ता, वी वांट टू गेट ऑफ द डिफरेंशिएशन value 2 coming from differentiating it. So supposing I differentiate with respect to wi, so what I will get? I'll get 2 over 2n, and there was a summation term, which is yi minus wi xi, and I differentiate it with respect to wi, so I'll get a minus xi. So this minus will make this positive. Okay, so don't worry about it. We are proceeding in the negative direction. अगर मैं y tilde minus y करूंगी तो ये differentiation मेरे पास में आएगा yi minus वो जो भी wi xi, which is y tilde into xi. So यहाँ पे वो negative आ जाएगा. It is automatically taken care of when we differentiate the error function. Is this okay? So what it is showing is the weight update is the previous weight plus the learning rate, which is a very small value because you have to take a small value, and the error, ये जो आया यहाँ पे error क्या आया, yi minus y tilde, ये जो first term आपके पास आई है, you differentiate the activation function, and then when you differentiate this, you get a corresponding xi. So that's what it is showing you the update. So what you do is you randomize the weight, initialize the weight, you feed forward the input, get output, compute the error, back propagate the error till the first layer, update the weight, feed forward the input. Feed forward the input is you are feed forwarding all the inputs, n inputs, and you are computing an average weight. So this is a batch gradient descent algorithm. The whole batch goes inside, and this one iteration is called epoch, where all the inputs are going till the end and computing a output. You are computing a error. You compute the error, back propagate the error, update the weight, keep on doing this till it is time to converge. When do you converge? When the magnitude of the gradient is very small and the error itself is very small. So you have a training, this is iteration, and this is training error. So the training error graph goes like this because it is a gradient descent. So error will always decrease. Mind it, if your error is increasing, then you are doing something wrong, because it is a convex function and it is a gradient descent algorithm. Every iteration the error will decrease. So this is your training error. So with iterations it keep on going down, and जब ये बहुत छोटा हो जाए, so I am saying when the error itself is very small, then this error itself is very small, number of iterations is very large, the magnitude of the gradient is very small, error का gradient बहुत small है. तो कई बार आपका ये stuck हो जाता है अगर आपका training error ऐसा आता है. It is not good to stop here because the error itself is very large. So you keep on iterating it till it goes down. Okay, so keep on repeating this gradient descent, feed forward the input, compute error, back propagate the error, update the weights, feed forward, compute the output, compute the error, back propagate the error. This feed forward back propagation algorithm. And we will stop here. Any questions?
So participants, you can write your queries in the chat box. Yeah, one question I could see, ma'am, is there any guarantee that gradient descent reach the local minimum point?
No, it will. The local minimum is the global point, and this is guaranteed because we are proceeding a small step in this direction. We are going down. हिल में अपन धीरे धीरे नीचे उतरेंगे और जब तक हमारा स्लोप जीरो नहीं हो जाता वहां तक हम जा रहे हैं, तो वो मिनिमम पॉइंट है. एंड इट इज अ कॉन्वेक्स एरर. This is a convex error. It has only one minimum, which is the global minimum. So it doesn't get stuck at local minimum. That's why we are taking convex error function.
Another point is, if the function is not convex,
Then
what should we do?
then there is a problem. So that's why you have to always proceed with convex error functions. क्रॉस एंट्रोपी होगा वो भी कॉन्वेक्स एरर फंक्शन होगा. अगर आप वैल्यू लेंगे वो भी कॉन्वेक्स होगा. अगर ये सॉफ्ट मैक्स लेंगे तब भी वो कॉन्वेक्स होगा.
So another question is, please share PPT. Yes, PPT will be shared.
Yeah, it will be shared. मैं अभी सर को भेज
So
दूंगी.
another question is, how do we decide the learning rate?
Learning rate, we usually, like this I said, we have to keep it very small. So for machine learning, this very small is like 0.0001. This is very small. This 0.01 itself is very large. So अगर आप ये करते हो, आप देखते हो आपका converge ही नहीं हो रहा. As I said, then it keeps on bouncing, and because there is no gravitational force, so it never comes down. So that's why we need to keep the learning rate very small, and that's what the issue is. If you have large number of layers in the network, the number of parameters are very large, and if you solve a small example, you will see, even if you take learning rate like this, we are proceeding very slow. There is a very small change in weights as the number of layers increases. आप देख रहे हो कि back propagation of error earlier layers में बहुत कम जाएगा. तो यहाँ पे वो जो ग्रेडियंट अपडेट है वो बहुत छोटी होती है. So it takes a lot of iteration, thousands of iterations before the network converge. But we are not bothered about that, because now we have machines, we have GPUs which can do the computation very fast, and every layer the computation is happening in parallel, because it is not dependent on anything else. We have the weight matrix, we have the input, we can compute the output in parallel. So usually, and it is a hyperparameter, we experiment and we learn कि किससे आपका बहुत स्लो हो रहा है, तो बहुत स्लो भी हमें नहीं रखना. तो यूजुअली क्या होता है कि व्हेन यू आर फार फ्रॉम द इनिशियली, लेट्स से योर एरर फंक्शन इज लाइक दिस, लेट मी शो इट हियर. तो अगर अपन यहाँ कहीं है, तो ये ग्रेडियंट अपना बड़ा होता है. तो अर्लियर जो स्टार्टिंग में हमारा लर्निंग रेट है, विद एवरी इटरेशन what we do is we divide the learning rate with the number of iteration. So as we approach the solution, the learning rate decreases. So शुरू में हम बड़े जंप ले सकते हैं, बट सॉल्यूशन को ओवर स्टेप नहीं कर दें, तो वो आपके पास में वो स्टेप साइज छोटा होता जाता है. That is one heuristic that we use. Sometimes they say that number of iterations का square root ले लीजिए. So you experiment with different values and you keep on updating the learning rate, but it has to be kept small. We assume that initially we are very far away from the solution, so you can have a slightly bigger learning rate, but as you iterate, you keep on decreasing the value of the learning rate. I hope you understand this.
Yes, ma'am. There are also how to choose the randomized weights in neural network. Will it
Okay, so
affect?
yeah, it will affect definitely, and because there was a part here ki what not to do when you are using weight initialization. So आपके पास में अगर कई लोग बोलते हैं कि जीरो इनिशियलाइज कर दीजिए, बट ये नहीं करना चाहिए, बिकॉज आप देखना इसमें कि when the ReLU activation function, तो every node will evaluate zero and there will be a no learning. सो आपके पास में जीरो इनिशियलाइजेशन नहीं करना चाहिए, कांस्टेंट इनिशियलाइजेशन भी नहीं करना चाहिए, बिकॉज देन एवरी नोड इन अ लेयर प्रोड्यूसेस अ सेम आउटपुट. सो दिस काइंड ऑफ बिकम्स, ये भी सेम आउटपुट निकाल रहा है, ये भी सेम, कोई और भी नोड्स होंगे तो ये सेम. तो ये इट एक्ट्स लाइक अ सिंगल, every layer acts like a single node, so this becomes a linear network, and which cannot solve non-linear problems. So random initialization with very small values, so वो बहुत जल्दी converge होंगे to very small values, so आपके पास में vanishing gradient problem आ जाएगा. और random initialization to very large values, वो भी vanishing gradient problem आ जाएगा. जब ReLU होगा तो slow convergence होगा, that is the training will take a lot of time. सो ये सब नहीं करना चाहिए, कुछ इन बिटवीन लेना चाहिए. सो रैंडम इनिशियलाइजेशन, एंड यूजुअली यू से जीरो मीन, गॉसियन डिस्ट्रीब्यूशन से जीरो मीन एंड स्मॉल वेरिएंस से आपको वेट को इनिशियलाइज करना चाहिए. पॉजिटिव वेट्स भी हैं, नेगेटिव वेट्स भी हैं, द वेरिएंस इज वेरी स्मॉल, बहुत ज्यादा चेंज नहीं है. एंड रैंडम इनिशियलाइजेशन, नॉट वेरी स्मॉल वैल्यूज, not very large values, because then there will be vanishing gradient problem.
Yeah,
So
I
you,
think there is another question related to that. Whatever you have discussed, how to deal with that, vanishing gradient and exploding gradient, you have already explained. Similar thing.
yeah.
So, how can trust on neural network in choosing weights?
How can we?
I could not able to understand. How can
Please
trust?
randomly initialize the weights.
Yeah. Yeah, that's all, ma'am.
And get it from a Gaussian, distribution with the zero mean, so that you have both positive and negative weights, and the variance should be small, so that there is not too much of variation in your weight initialization.
Yeah.
So when vanishing gradient happens, we drop like some of the nodes, the gradient becomes zero. So वो कुछ learning में मदद नहीं कर रहा, तो such nodes we use some dropouts. So हमें नहीं मालूम है कि which node is has gradients has vanished. So we randomly use dropout to overcome this problem. एक क्वेश्चन आया था अभी तो मुझे वो दिखा. I hope this is okay, Deepak.
Yes, ma'am. Absolutely, absolutely. Almost all the
So,
questions have been answered.
and they have an idea of deep learning. Now
Yeah,
this
yeah, yeah. At
network
least they got
with
the idea.
multiple layers
Everything
is
they got.
deep learning.
Everything they got.
Yeah. The activation functions and all these terms which will be used in your deep learning, which will be happening in your computer vision course. So I'll share the slides with sir and he'll share them with you. Okay.
Yeah, we'll upload it in on Canvas actually. So thank
Yeah.
you so much, ma'am, for a wonderful lecture on overview of neural networks as well as the deep neural networks and deep learning. I hope participants have got at least the idea how
Yes, sir.
actually this neural network is helping in solving problems.
Yes.
And you can easily connect, as ma'am said, you can easily
Mhm.
connect your other lectures like convolutional neural network with whatever you have
With.
studied today, right?
Mhm.
So thank you so much, ma'am, for joining us, for sparing your valuable time. Yeah, thank you so
And
much.
then I like to mention wherever it is written fully connected layer, that is this layer, which we have talked. That multi-layer neural network is the fully connected layer where you learn the weights. In all the
Yes,
convolutional networks and जो भी deep networks हैं, जहाँ पे भी आपके पास में fully connected layer शब्द आएगा, that is this multi-layer neural network where you learn the weights. Okay,
done.
then I
Okay, ma'am.
okay.
Thank you so
Thank
much.
you. Thank you. Thank you.
So thank you to all the participants for attending all the sessions today. So again, I will request the same thing, that please attend all the sessions, because all the sessions are very important, and even I think attendance is also a mandatory thing here. So and again, at the same time, you can learn a lot of things from different speakers. You can interact with them. You can ask your questions. Okay, thank you so much. We will meet tomorrow. Good night. There is little bit actually modifications. I mean in the timetable, I mean, especially the schedule, right? So I will share with you today. No, I mean tonight. Some of the speakers have rescheduled their lectures, so I'll just send you the updated one tonight.